Hi everyone, welcome to Module 5 for MA 215 Applied Statistics at Bellevue University. This week and next week our focus is on probability and probability models. So we're going to take it slow through this week and next week, so you'll find that there are not many videos this week. So please make sure you watch them all. Focus on doing the practice activities. So again, we're going to talk first about random phenomena, and we have talked about randomness already and what makes something random. But remember, an event is considered random if we know what outcomes could happen, but we don't know which one will happen, like rolling a die or flipping a coin. There's a lot of terminology when it comes to probability, so I've tried to sort of set those apart by using an orange font, but these are the terms that you need to know and understand for probability. So first we have experimental probability, or empirical. Those are the same thing. What's important to note is that this is the long-run relative frequency, which means essentially we're performing an experiment of some sort, or we're collecting data. And so what we're doing is based on actual data, not based on what we would expect to happen. Each trial has an outcome. So if we were looking at the experimental probability of flipping a coin, and the trial would be flipping the coin, the outcome would be heads or tails. All of the outcomes combined, so all of the outcomes that you get, not just heads and tails, but all of the outcomes that you get are the event. So the list of all possible outcomes is called the sample space. So if we were flipping a coin, that would just be heads, tails. If we were flipping two coins, that would be heads, heads, tails, tails, heads, tails, tails, heads, etc. Trials would need to be independent if we're going to look at experimental probability, unless we have a very large number. Independent means that when I flip the coin, then the next flip of the coin is not going to be changed by whatever I got the first time. So something where it would not be independent is, say, drawing a card out of a deck. If I draw a card out of a deck, then the next time there are only 51 cards to draw from instead of 52, and so those are not independent. The last one is theoretical probability. This is the probability that you're used to. The probability that each event in the sample space will occur. It's not based on actual data, it's based on probability theory. So it's based on what we think will happen. So if these are the four options, assuming there's a 50% chance of getting heads or tails each time, this would be a 1/4 or 25% chance, 1/4 here, 1/4 here, 1/4 here. Okay, so this is the theoretical probability. The experimental probability is what would happen if I actually flipped two coins several times and recorded how many times I got heads, heads, how many times I got tails, tails, etc. That would be experimental or empirical probability. So let's take a look. This is an empirical probability situation. So each day on the drive to work, we pass through an intersection. We check to see if the light is red, green, or yellow, and then we just keep track of it. So the very first day, the light was green, and I'm tracking what percent of the time I get a green. So far, I'm at 100%. 100% of the time it's green. The next day, it's not green, it's red, and that means one time out of two, because now it's 2 days, I got a green. So that's 50% of the time. So notice I've plotted the 50%. Day 3, I get a green. So now out of the 3 trials, 2 of them were green, so 0.67, which is here. The next day I get a green, so 3 out of 4, 75% of the time. Day 5, yellow, etc. And I keep following that pattern. And what do you notice about this? Notice that it keeps going and going and going, and it's sort of evening out in here a little bit. So my guess is that about 33% of the time, and again, that's not super accurate because I don't have a lot of scale going on over here, but 33% of the time in general, maybe 32, maybe 31, obviously I would need to see the actual numbers, that's about what I would expect to get a green. This is essentially the law of large numbers. The law of large numbers states that if essentially we do things in the long run, meaning it's not just 1 or 2 times, because if I stopped after just a few times, I wouldn't really be able to pin down because I had 100 and then 50 and then 67 and 75, etc. So it's the long run relative frequency of independent events. So the law of large numbers essentially says that that's the probability as long as each trial is independent, which of course it would be. because we're just looking at the color of the light. So that's the law of large numbers. Here is the law of averages. So I have 9 beautiful nephews. It's true, I have 9 of them. No nieces at all, just 9 nephews. So if a sister-in-law of mine were to get pregnant, then I'm certainly going to have a niece, right? Or if I flip a coin 10 times and I've gotten tails each time, then I'm due to flip a heads on the next flip. What do you think? Well, that's the law of averages, and obviously it is absolutely false, because each time a sister-in-law of mine has a baby, theoretically, there's a 1 out of 2 chance of a boy and a 1 out of 2 chance of a girl. And it doesn't matter that I've had already 9 beautiful nephews. It just matters that the next time I still have a 1 in 2 chance of getting a boy or 1 in 2 chance of getting a girl. Same thing for flipping a coin. On the next flip, I still have a 1 out of 2 chance of getting a heads, even though I've already gotten tails each time. So because the trials are independent, we have the same probability. So again, independent is very important, meaning that one outcome doesn't affect the next.